So in this video we're going to start looking at volumes as opposed to area, and that might seem kind of a lofty goal considering that volumes are three-dimensional and the integral's been defined in terms of area for us at least. But there are ways to actually use the integral to determine volumes, and it kind of gets at this idea that you want to view the integral as a tool that sums. And so whether we're summing areas of rectangles or volumes of little disks, we can still use the integral to do that. So the first technique, and I apologize for this very poorly drawn pyramid, this is supposed to represent a 5-meter high pyramid standing sort of resting on its side, where the x-axis is going right through the center of the right through the center actually of the square cross section that you would make anytime you would cut this perpendicular to the x-axis. So this is supposed to be a 5, and the idea is that we need to get the volume of this thing. Now the first thing to notice is that it is a pyramid, and we know the formula for a volume of a pyramid from geometry. It's 1/3 x squared, where x is the length of the base, times the height. And so the actual volume of this thing is going to be 1/3. The base is, according to the description, it says that the base is 5 meters on each side. So each side here, or the base rather, has a length of 5. So the base of the pyramid is the square base, has each side being 5, and then the height of it is 5 as well, even though it's not sort of drawn to scale here. So the actual volume of this thing we know ahead of time, but we'll compare it to what we get when we do the integral. 125/3. The way the method of slicing works is you imagine placing this pyramid on the x-axis as is indicated here, with the x-axis going right through the center of it. And what you do is you cut a slice of this pyramid perpendicularly to the x-axis. So when you do that, kind of zoom out here, you're going to get and I'm going to indicate that this slice has some thickness. So it's almost like you just sliced a piece of bread here, right? So what we want really is we want the volume of this one representative arbitrary slice. And then what we're going to do is we're going to sum those slices as our x value goes from 0 to 5. Right? So we're going to be summing up all these volumes as x goes from 0 to 5. And that's where the integral comes in. So the length and width of each of these things is going to be x. And the reason you know that is because when you're 5 meters from the x-axis, from the origin rather, the side length of the square that represents the base is 5 meters. And so when you're x units from the origin, we would expect by proportional reasoning that the size would be x. And it took me way too long to get that out. Sorry about that. So the thickness here would be represented by dx, since it's a small change in x. All right, we want to represent that thickness as the differential. And so now what we do is we just sum up. We're going to sum up all of the volumes of all those rectangles, or slices rather. So this is a volume equal to x squared times dx. We're summing all those as x goes from 0 to 5. And now we can use the fundamental theorem. So you take an antiderivative and you get 125/3, as was expected. All right, so as long as we can model the volume of an arbitrary slice from this pyramid, like we did here, we can just sum those slices up as x goes from, in this case, 0 to 5. And we end up getting the exact same answer as we got when we just used the formula itself. So that's one small example of the type of thing we'll be doing although in the next few examples we'll be doing solids of revolution. But we still use this idea of slicing sections of these solids in order to analyze the volumes of those cross sections, and then we sum them all up.